I am Tangashakti from Triple Department, Rogini College of Engineering and Technology. Subject name is Digital Signal Processing AE8591. In this video, we are going to see the analog filter design with Butterworth filter. So here we can understand the concept of Butterworth filter and how to design the Butterworth filter. So first, before that, we should know what is meant by Butterworth filter. So the Butterworth filter is a special type of signal processing filter designed to have a frequency response as flat as possible in the pass band. So it's having flat response in the pass band, in the range of pass band. So this is the response of the Butterworth filter. So next we are going to see the design of Butterworth filter. So first, to design a Butterworth IA or digital filter, first an IA analog Butterworth transfer function is determined. First step, we have to determine the analog Butterworth filter transfer function. Next, this filter transfer function, analog transfer function, is converted into digital filter transfer function by using either impulse invariant or bilinear transformation. With the help of impulse invariant or bilinear transformation, we can convert analog filter transfer function into digital filter transfer function. So already we know that the Butterworth filters are defined by the property that the magnitude response is maximally flat in the pass band. So in the range of pass band frequency, the magnitude will be flat. So this is the property of Butterworth filter. So next we have to define omega p. So the omega p is nothing but pass band edge digital frequency. So that will be represented in radian per sample. And omega s is the stop band edge digital frequency. That is also represented in radian per sample. And here the sampling time. So the sampling time is the reciprocal of sampling frequency. So it will be represented in second. And Fs is the sampling frequency. It will be represented in hertz. And AP. So AP is the gain at a pass band frequency omega p. And also AS is the gain at a pass band frequency omega s. Next, here this is the pass band edge analog frequency, and this is the stop band edge analog frequency corresponding to omega s. So these are the specifications of the Butterworth filter. So next, for designing Butterworth filter, first you have to choose either bilinear or impulse invariant transformation and determine the specification of analog filter. So if you are choosing the bilinear transformation, means we have to select the pass band analog frequency equal to 2 by 2 tan omega p by 2 and stop band analog frequency equal to 2 by 3 tan omega s by 2. So this is the transformation equations for the bilinear transformation. For the impulse invariant transformation, pass band frequency equal to omega p by 2 t and stop band analog frequency equal to omega s by t. So with the help of analog and with the help of bilinear transformation and impulse invariant transformation, we can choose any one method to convert analog transfer function into digital transfer function. Next one, determine the normalized transfer function Hs of n of analog low pass filter. So here when n is even, so the normalized transfer function equal to pi k equal to 1 to n by 2 1 divided by sn square plus bk sn plus 1, and for the n value odd means here we have the expression Hs of n equal to 1 by Sn plus 1, pi k equal to 1 to n by 2, 1 by Sn square plus bk Sn plus 1. Next one, calculate the analog cutoff frequency equal to omega s by analog sample frequency divided by 1 by as the whole square minus 1 the whole power 1 by 2n. Next step, determine the unnormalized analog transfer function h of s of low pass filter. So h of s equal to, we are converting unnormalized analog transfer function from normalized transfer function. So you have to substitute Sn equal to s by cutoff analog frequency. So here when the order is n is even means h of s is obtained by letting s n value changes to s by cutoff frequency. H of s equal to pi, k equal to 1 to n by 2, 1 by Sn square plus bk Sn plus 1 for the value of Sn, s by cutoff frequency, analog cutoff frequency. For the order of n is odd means h of s is obtained by letting s instead of n you have to write s by cutoff frequency. So we will get h of s equal to this expression. So here we are converting unnormalized analog transfer function into the, we are determining the unnormalized analog transfer function h of s. So here for the n is even order, for the n is odd order, we have the different equations we have to substitute here. So we have to calculate unnormalized analog transfer function. Next one, determine the transfer function of digital filter. So here we have to use bilinear or impulse invariant technique. We can choose any one technique to convert analog transfer function into the digital filter. Next one, realize the digital filter transfer function h of z by a suitable structure. So after getting the transfer function of digital filter, we have to realize the IR filter. So for the realization of IR filter, we have direct form realization, cascade and parallel realization. We can choose any one technique to draw the suitable structure, to draw the structure of digital filter transfer function. Next step, we can verify the design by sketching the frequency response h of e power j omega equal to h of z into z equal to e power j omega. So here the basic filter design is a low pass filter. So from this we can get high pass, band pass or band stop filter by frequency transformation technique. Okay, thank you.